Hi everyone. In this video we're going to be going over all the aspects of our circuitry. We're going to start with an overview of the circuit, the different components used, how it's actually going to be operated. Then we're going to go through and actually build that circuit. We're going to use a toner transfer method on PCB. So what we do is we start with this copper PCB. We print out the circuit onto a toner transfer paper, which is a thermal paper. We put that onto the copper, we put it into an acid bath. The acid eats away the copper that's exposed, and then the copper that's under the toner gets preserved, and in the end you're left with a circuit. And then finally we're going to put that all to the test, hook it up to the Pi, make sure everything works as expected, and we should be good to go. So let's get started.
So this is an overview of the circuit we're going to be building. This is the PCB view, which is the printed circuit board view. So rather than using a schematic or a diagram, this is the end result, what we're going to be building, what we're going to be soldering our components onto. Since we have 4 pumps, there's 4 different controls in this view. So to make things simpler, we're going to isolate just one of the pumps, talk about the components there, talk about the different circuits, and then we can expand that out to the 4 different pumps. Now that we've isolated the circuit to just one pump, we can talk about the inputs. There's 3 different inputs for the circuit. There's the ground wire, GPIO pin coming from the Raspberry Pi, and then there's an input voltage, which is the VCC here on the diagram. Now for the components that we're going to use. First off, we're going to use a 2-pin terminal block connector, and we're going to use 2 of those. We're going to use this single pole double throw relay, a NPN transistor, a diode for protection, 2 resistors, a 10K and a 1K. There's 3 distinct parts to the circuit that we want to talk about. The first being the 120 volt AC line that is coming from the house. The second is that constant voltage coming in from the Pi. And finally, the third being the circuit controlled by the Raspberry Pi's GPIO pin that goes to the transistor. So the first circuit we'll talk about is that 120 volt AC line coming in from the house. That connects through the terminal block and into the single pole double throw relay. And when there's no voltage applied to the top of that relay, then what's going to happen is that relay is going to be in the normally closed position, which is an incomplete circuit and doesn't allow any current to flow through the system. When a voltage is applied to the top control circuit, that switches the relay from that normally closed position to the normally on position. And in our circuit, this turns on the valve, opening the solenoid and letting water flow through the sprinkler system. And when we're done watering, we remove that voltage from the top of the control circuit, which then switches the relay back to the normally closed position. The voltage is removed from the solenoid closes, and then water is no longer flowing through the valves. So the next part of the circuit that we'll talk about is up here at the top and involves the GPIO pin coming off the Raspberry Pi. You can see that there's 2 resistors involved, and that this part of the circuit is really about controlling that transistor. So the normal operation when there is no voltage on the GPIO pin, essentially any voltage that's left in that circuit is going to drain through that R4 resistor and just go out the ground. However, when that GPIO pin goes high and applies a voltage, that voltage is going to travel through the R3 resistor. It's going to interact with the transistor, turning that transistor into an on state, and then also drain out through the ground. When it turns that transistor into the on state, that's where the other part of the circuit is going to come into play. And it's important to note that that GPIO pin cannot take a large current. And that's why we use that transistor. It isolates this control part of the circuit from the other part of the circuit, which is switching on and off that single pole double throw relay. And even though they both use 5 volts, the current can be different on that part of the circuit that's traveling through the single pole double throw relay. And this transistor just helps isolate that and protect the GPIO pin from being shorted out. Which brings us to the last part of the circuit, which is doing the switching on and off of that single pole double throw relay. It takes a standard 5 volts in, and its normal position is that circuit is open. Because that transistor is going to be acting like a switch, and if the GPIO pin is not high, then that switch is essentially open, which won't allow the current and voltage to flow through the system. However, when we want the water to run and we switch that GPIO pin high, that completes the circuit, which then allows that 5 volts to flow through the single pole double throw relay and through the transistor exiting out the ground. And of course, when that happens, that switches the single pole double throw relay into an on state, which allows that AC voltage and current to flow through the system, which will open up the solenoid valve and allow water to flow through the sprinkler system. And one last piece of the circuit to note is that diode, which is above the single pole double throw relay. And what that diode does is essentially allow current to only flow in one direction. So as the system is on, there is a voltage and current flowing through the system. When it turns off, because of the induction that it uses in the single pole double throw relay, you can essentially have this kind of kickback current where even though you've now turned that off, the voltage is still flowing through the system and wants to reverse direction. The diode allows that to happen and acts like a traffic cop and essentially directs that voltage safely through the system so that it can exit out a ground wire without shorting out any of the system. So that about wraps it up with our circuit. Hopefully now you can see how the 3 pieces that we've gone over combine together to control those solenoid valves in our system. The GPIO pin of the Raspberry Pi uses the transistor to isolate itself, and then that transistor switches on and off the circuit that flows through the single pole double throw relay, which allows the AC circuit to turn on and off, putting power through our system. So the next steps are using that toner transfer method to create our circuit board. We're going to need to print our circuit onto the toner transfer paper. So we start with the toner transfer paper and we have to separate that out. It has this kind of protective coating that protects the print surface that we're going to need. So we peel that back sort of like a sticker, and that exposes the print surface that we're going to want to print onto, and then we simply load that toner transfer paper into the laser printer with the correct side facing up. So once we've printed our circuit onto the toner transfer paper, we simply cut away the excess so that the size of the paper is a little bit smaller than the PCB board that we're going to be putting it onto. And then our PCB board needs to be prepared. We need to clean the surface, make sure there's no deposits, and then we want to scour that surface. We want to lightly sand it with a sandpaper evenly, just to make sure that there's essentially a roughed up surface that has some grip. So when we apply the heat to the transfer paper, it transfers smoothly. Now we want to make sure that the transfer paper is securely fastened to the board. I like to use a painter's tape. I found that if you use anything like a duct tape or like a scotch tape, as you apply that heat can essentially melt the tape and it leaves a kind of gooey residue from that sticky surface. And that just kind of messes up the board and allows the acid to not really eat through where it needs to. And somehow, because painter's tape doesn't have as sticky as the surface, it keeps the transfer paper firmly in place, but doesn't leave behind a nasty residue. And then we apply the heat. We use an iron for this on high. And you want to be making sure that you're applying heat to all parts of the toner transfer paper and as evenly as possible. So I like to press firmly on it and then weigh it down with something like a dumbbell or some kind of heavier object to make sure that the iron is really pressing on the toner transfer paper. And then I let it sit for a few minutes, like 3 to 5 minutes, to give it adequate time to really heat that up and transfer that toner onto our PCB. Then you have to be careful because then the board is actually really hot. So make sure you're taking the proper precautions or allowing it to cool before you try to handle it. Once that board is cool and safe to handle, you want to remove the tape and start peeling back that toner transfer paper. And hopefully at this point you're left with a good image that is transferred onto the PCB. All your lines and connectors are solid, thick, no breaks in them, and everything has kind of gone according to plan. If there are some breaks or the image didn't transfer as well as you would have liked. You can use a trick of using like a Sharpie-like marker to trace along those lines, and that'll actually add a little bit more substance that will protect from the acid, and the acid will eat away around it, but not necessarily through that Sharpie marker. So that is an alternative that you can use if the transfer didn't go exactly 100% according to plan. And then the next step is into the acid bath. So for our acid bath, we're going to be using muriatic acid, which you can get at a hardware store. It comes in about a gallon container, and we're using hydrogen peroxide, which you can get just about anywhere, like a supermarket or a drugstore. And the ratio is going to be 1 to 2, 1 parts muriatic acid to 2 parts hydrogen peroxide. And then once we have that mixed, we're just going to dunk our PCB board in there and let it sit. Luckily, the process is kind of slow, so it'll take some time to eat away that copper and completely burn out our board. So as the board sits, occasionally you can kind of pick it up with some tongs, agitate it in the acid bath to kind of move away that copper that has already been eaten away, and let the remaining layers of copper get exposed to the acid and start to be etched. Finally, once our board is completely etched, we dunk it into just a hydrogen peroxide bath. That'll remove any of the hydrochloric acid that remains, and then that board will be essentially safe to handle and ready for the next steps. So the next steps in preparing our board is to clean off that toner that remains on the PCB. We can do this using some acetone. Just wipe it away. I like to use gloves for that because acetone is kind of a nasty substance. But we can just essentially apply that, wipe away the toner, apply some more, and just keep applying and wiping away the acetone until we're left with a PCB that just has copper on it. Then using specialized drill bits, we're ready to drill the holes for our components. And then once those holes have been drilled, we can thread our components through those holes and solder them to the board. At this point, I also like to use a multimeter to test all the connections, make sure all the paths don't have any breaks in them. And if need be, if there is a small break or a narrowing in a path, I can use a little bit of flux and a little bit of solder to help kind of reinforce that path. And once we've completed all those steps, our circuit is good to go and ready to be hooked up to the Raspberry Pi and tested in the system. So our circuit goes right into our enclosure with the Raspberry Pi, the USB power adapter, and our terminal block to hold all the wires. So the connection to the Pi is pretty straightforward. Instead of using a USB connector to power the Pi, instead we're using an alternative approach, which is to take the 5-volt line and ground line from the power converter and plug those right into the GPIO pins on the Pi. And as we've covered already, for our circuit, we need a 5-volt line, we need a ground line, and then for each of those solenoid pumps, we're going to use a GPIO pin to control it, and those are the orange, purple, yellow, and green pins on the Pi. All of our electronics are placed in a waterproof enclosure that is mounted on the side of the house. And then the wires that are connected to the solenoid valves go through a waterproof conduit over to the solenoid valves. Mounting our pumps and valves is a little tricky due to the size of the valves, the angles on the valves. They have to be raised off the surface. So we've used some pieces of 2x4 to kind of pull them off the boards and give ample room. Then all the wires from the solenoid valves just go up to another waterproof enclosure, and that is the other end of the waterproof conduit as well. Inside our waterproof enclosure, we have a bunch of wires. Each of the solenoid valves is going to take 2 wires. One is the hot wire, which is going to be the source of the AC current coming into the pump. And the second is going to be the return for that, which is the neutral wire. And you can see we use screw terminals to connect those wires. That just gives us the advantage of being able to disconnect pumps from the system very easily without having to kind of cut wires or unsolder anything. And then finally see that we have a string going through the weatherproof conduit. That's just a pull, so if we need to run new wires, we can just essentially take one wire on one end, tie it to that string, pull it through the system, and that way we've run a new wire. And that is all the major components of our system.
Thanks for watching. We hope you enjoyed this video. If so, let us know by hitting the like button. If you have any questions or comments, let us know in the comments. And of course, if you want to be notified of videos like this in the future, please hit the subscribe. That goes a long way in supporting this channel. Thanks and see you next time.